Okay, so for the fluent part, these are settings. You can see here that the solver will be pressure based because the density is constant, and so pressure based solver deals with when density is constant or flow is incompressible, and density based solver is when the density is variable. And because the flow is transient, because it is developing with the time, so we will make it transient. And the gravity is in the z direction. So this is a very important thing. What does it mean is that the gravity is not always in z direction, but depending on the coordinate system. For example, tank is made in this way, and let's say we have the z-axis is pointing upward. So positive z-axis is pointing upward, and we have the x-axis over here, and the y-axis is over here. So the plane on the bottom is the xy plane, and the direction in the height is the z direction. This is positive z direction, and because the gravity will be affecting on the downward side, so we put the minus sign that to represent that this is going to be in the minus z direction. So instead of putting the plus 9181, we will putting the value the minus 9.81. But if the direction is reversed, for example, if we use the instead of the xy plane, if we use the, let's say, the zx plane on the bottom side, so what will happen is that, so let's say now we have the y-axis is on the top side, we have the z-axis and x-axis over here. So in this case, we will define the gravity in the y direction. So gravity will be y direction, and value again will be minus 8.18 meter per second square. So I hope this is clear. Okay, so these are all settings. You can see the materials are air and water liquid. Model is a VF, volume of fluid, and so we will use the two phases, air and the water liquid. And boundary conditions are on the circular and bottom wall as a no slip, or if it's the top boundary as a pressure outlet. Operating conditions as discussed here, gravity is this one, and density we are going to define is the density of the lighter fluid. So logic is that because lighter fluid will be prevailing there, and so reference should be from that fluid. It will make the simulation very stable. So if you make the operating density of the heavier fluid, this will make the instability in the problem. And also this is also another thing is that the primary fluid will be there for forever. So the secondary fluid, which is secondary phase, is water. So that water will be drained out from the geometry, and this will be filled with the air. So that fluid which will be there is density should be defined there. This is one second logic. And we use these turbulence models, simple for the velocity pressure coupling, and these schemes for the different things here. So I will initialize with the default values. So 0 are for our variables except the turbulence quantities, and the phase to volume fraction will be equal to 1. That is the water. In this case, air is the primary phase, and we will create the solution animation. And so I want to see that how this will be draining with the time. And time step I will decide based on, because we have done the calculation that it will take the 4.3828 seconds to empty a tank. But take into consideration one thing. When the fluid is over here, means this is a full. So at that time, this will have the high pressure. This will have the high pressure. So pressure is the rho GH. So potential energy is a rho GH. So with the high pressure, the rate of water from the bottom will be higher. But as the level is going down and down and down, this energy will be lower, and it will be pushing the energy less and less energy from there, because the G will be same, density will be same, but height is reducing. So with the height reduction, the pressure will be difference will be lower, and the volume rate flow rate will be decreased. So you can accept that it's expected value that with when the tank is full, the rate of flow will be higher. So you will see that it take less time to empty a tank for the first maybe 1/3, 3/4, and it will take more time to empty tank from the remaining 1/4. So this can be expected value. And another thing is that the time which we are showing here, 4.382 seconds, this time may be less in the CFD. Why? Because this is assuming to be the very simple analysis, analytical analysis, but in the CFD, actual values will become there. Maybe the difference maybe is that instead of the 4.38, the tank may empty within the maybe 3 to 4 seconds. So let's see this thing. So let's say now we divide this into the 2000 time steps. So therefore time step for the one iteration for the one will be equal to 0.000219 for 1 seconds. So now instead of draining tank in a one time step, basically we are dividing into 2000 time steps. So it will take 2000 time steps to drain the tank from the initial height to the final zero height. But here I will be using the adaptive time stepping in this workshop. So what is adaptive time stepping is that it will take into consideration about the many things. So for example, if the solution is encountering a problem in converging, so if the initial time step was 0.01, so this will reduce the time step maybe to the 0.008. And still solution convergence criteria, which we'll set is 10 power minus 4, is not achieved. In that case, it may go to the 0.005. So what is the criteria for this time stepping is that if the solution is being converged in 10 power minus 4, let's say in the 18 iterations. So what will happen is that the time step will be reduced. But if it is taking the all iterations, the time step may be, so if it is increasing in the less iterations, the time step will be increased. So 0.001 may be 0.02. But if it is converging in the less iteration, less than 20 iterations, so it will reduce the time step so that the number of iterations would be 20. When it is requiring 20 iterations to fully converge to this value, this will not change any time step there. So if it is converging faster, it will reduce the time step. It is converging slowly, difficult with the difficulties, it will increase the time step. It will decrease the time step. So this is clear, I think. Okay, so this all discussion has been done. And one more thing is that current number, I think you are aware of this thing. This is the ratio of the mesh and the time. So if the current number is less than 2, it will be keeping the time step constant. This is also another criteria. And in case that the time step is very large, and if the current number is 250 or more, the solution will be stopped and you have to make the new setting, maybe new mesh, and start from the scratch. Okay, then finally we will have these results. You can cut the one plane from the middle, and also I will show you that how you can make these type of the figures and then the contour plot in the middle. And this animation which you can see over here. So you can see that the flow is draining initially with some slower pace, and then it will take the speed. Okay, then finally it will be draining like this. So now because the flow height is very, very low, so it will start to flow first from the middle, because the energy will be lower on the both sides and high energy on the middle side. Like this.